Welcome to Applied Houdini Volumes 1 Fundamentals. In this class, we're going to talk about what volumetric simulations are and how they work, including what voxels are, what vectors are, what velocity fields are, basically all the nuts and bolts of really understanding what's going on in a simulation rather than just relying on presets to get you to something. I want you to understand what's going on behind the scenes so that you can make production quality effects more easily and more confidently, and at the end of the lesson we'll end up with a bunch of smoke in the shape of a pig head moving around like you can see here. So without further ado, let's go get started. Alright, let's get started moving volumes around in Houdini. First things first is we want to set up our project. The project is not the file itself, the project is just the kind of directory on your disk. We'll call it something volumes 1. And for me, version 2, because I did this 2 years ago, and now we're doing it again, even better. So here it is. So you can see it's going to create this directory on your disk. It's going to make all these subdirectories that are just for organization's sake. This is not the actual Houdini file itself, which is the HIP file. Say File, Save As, and click Job. That will bring us to this variable. This $sign thing is a variable, and that refers to that directory that we just made. So again, the project area. So volumes 1.0, and I'll just increment the 0 as we save things, or maybe I won't. I should, but I probably won't. So good. So we have the file saved. We have the project set up. Let us now set up the bare bones of what we're even trying to do. In here is a network view, where we're going to drop our nodes down here by pressing Tab and starting to type something like pig. And you'll see test geometry, pig head. And there it is. And what this does is it creates actually a generic geometry node. Any geometry, in our case, polygons. You probably know what polygons are, but maybe you don't. Polygons are these little flat squares, or really triangles. There's 2 triangles for each one of these squares you see. And they come together to form the shell of a piece of geometry. So hence this is called a geometry node, and inside of it we have more nodes that generate the geometry itself. So again, this is a container that has a position in space. It can rotate whatever's inside of it or move it with translate. Well, it looked like it was getting bigger. Really, it was coming at the camera. You can see translating it changes it there, like so. And the actual thing that made the polygons was this pig head thing here. There's a few different difficulties on it. Difficulty only really means, like, a hard difficulty means that this thing is hollow. Some tools don't work well with hollow pieces of geometry. Medium means that it is now sealed, but it's still kind of high res and has textures on it. You can see the pig skin and everything else. And low, or easy rather, is super simplified and no textures, and it's sealed. For our purposes, we'll just keep it on medium. So there it is. I'm going to jump back out to the main scene by pressing the object area. The object area stores all of our objects. This one right now is our pig head. And by holding the spacebar and right clicking to zoom in and out, middle click to pan, and left click to rotate, all with the spacebar, we can move our camera into some kind of position where we will see the pig head framed in a nice way. And under the lights and cameras tab here, press Control on your keyboard and click on camera. And you can see now we're looking through a camera. And there it is. It was created here, also in the object area. The camera has a translation and a rotation based on where our perspective was before we control clicked it. Now, I find there's still too much space maybe, or I want to change it. If I try to move the camera again by holding down space and let's say zooming out, I'll actually pop out of the camera. And there it is, left behind. Kirk Cameron. But, is that right? Kirk Cameron? I'm not sure. Anyway, I'm back in it now by clicking on this and choosing our camera again. If I want to move the camera and have it actually update our camera, click on the lock, and now you can see it is updating the parameters here for us. Now why did I create a camera when there's already, I'll turn that off again, when we're already in a camera out here, because we need to designate an actual permanent camera when we're going to render this. When we're going to actually create images, final images, we need to have a permanently dedicated camera for that. So I'm actually going to move this a little bit more over here. Obviously, we can always move this later, but that's enough for now. So one more thing I'd like to do in terms of setting up the scene is we have our network editor here with our nodes, and we have the related parameters here. If I make this bigger and click on this little arrow up here, split pane left and right, like so, for both, now we have two sets of them. So now what I want to be able to do is I want to be able to have two different nodes as parameters visible at any given time. Or maybe I want to be inside this node here, but still back in the main scene here. So now we've almost done that by setting up the two columns, but we can do better by actually clicking on this tack, holding, and changing these to ones and these to twos. Basically what this is doing is, as you might have guessed, the twos are associated with each other and the ones are associated with each other. So I can click on the camera here, I can click on the geometry here, I could even just be inside of it here, where I'm inside the test geometry pighead here, but still at the object level here. Whatever I clicked last will be what it shows up over here. We could also peg this to 1 or 2 or whatever, but I like keeping it on the last selected node by default. Great. So we are set up and ready to go. Okay. So right now, this node is called test geometry pighead. I'm going to rename it to be source, because of course the purpose of this lesson is to make a volume simulation. So we're going to create a volume, put it into the simulation where it will move around, and then we will render that into final images. So again, starting with this is what's going to go into our simulation. Now, these are polygons, as I said. You can see the individual ones here. I can move them around. I could isolate it and just look at it forever, and it's wonderful, isn't it? A nice polygon. But we don't care this time. No polygons. So let's go back into the camera. What we want to do is volumes. Now, one of the many reasons that I'm re-recording this lesson is because there's lots of newer, better ways of doing things now. So the old way we would have done it is with ISO offset to create a volume, and I'm not even going to talk about it because we're not going to use it. VDBs are the name of the game now. VDBs are a very specific kind of volume. Now, I haven't even told you what a volume is yet, but I'm going to say VDB a lot, so I want you to know that for the purposes of this first lesson, VDB and volume are interchangeable. VDB from polygons, as I said, this were polygons, is going to create a volume, a VDB, from the polygons. So connect the output of that to the input of this, and then if we click the blue thing here to move our, this is now what's being evaluated, everything leading up to this, we have a weird looking pighead. This is a certain kind of volume that we're going to talk about a lot later. It comes up quite a bit in effects, and it's called a surface VDB or a distance VDB, or more commonly known as a signed distance field. We don't care. Turn it off. Turn this on. Fog VDB. Now we can kind of almost see a pighead in there. Almost. If I click on this pink, if I hover over this and click on this kind of pinkish looking one, I'll see the outline of this node. So you can kind of see the fog, as it were, the kind of volume that we're doing, is kind of in there. If I were to make the voxels, well, I didn't even say what a voxel is. This is as good a time as any to talk about what voxels are and what volumes are. So save it and just follow along. I'm going to show you something. I already made these in advance. So what are voxels? Polygons are flat little things that make up the shell of something. But voxels are chunks, are actual like cubes inside of an object. So it's pretty easy to conceptualize if we think about pictures first. Pictures have pixels. we know that a picture is made up of lots of little squares. And together, they have color stored in each one. And the more and more and more and more of them we have, it forms up an image eventually. Oops, did I do that? So what I'm demonstrating here is when we only have 4 by 4 pixels, each square is a pixel, we have, well, apparently I had it tallied incorrectly, but just to apparently subtract 1 from that. We have more and more resolution the more pixels we have. Like so. Until we get to a point where we're happy with it. So obviously, each of these squares stores data. It's storing a color value. That takes up memory on your computer. The CPU has to do something per pixel, and that takes time. So the eternal struggle in visual effects is finding some kind of balance. Some kind of balance between we have enough of these things that we can see what we want or that it looks good, but we don't want so many that the increase in quality is only a little bit. Like, check this out. From right here, let's say on 192, where I have 191 rows on each side, I have 36,000 bits of data, individual data that need to be stored. And if I jump up here, I now have 58,000. That's a huge increase, but look at the difference in quality. It's not much, is it? So it just depends. If we could have a billion rows and a billion columns to have an infinitely perfect picture, and we would. But we can't. We are limited by the memory of the computer. So in practice, we need to figure out what's the best trade-off. Now that's pixels. That's for a flat image. As you might have guessed by now, or maybe not, voxels are volume pixels. They are simply pixels that have a third dimension. They're cubes instead of squares. So here's the pig again. And you can see it's the same idea. Except that this time there are 3 dimensions, which means that while the pixels increased to 58,000 pixels by the end of this, because it's just flat, this is insane. Because we now have to multiply this number by this third number, the z, the depth. So it's literally exponential. It's an exponential increase. Every time we double the resolution, we are multiplying the total amount by 8. Because it's 2 on each axis. 2 times 2 times 2 is 8. So it's really problematic towards the end here. Again, here this looks like something. And then if I jump to here, this looks like something. But look how many more voxels there are from here. Look how fast it goes up at the end. If I literally just play it through, you can see how slowly it's going up. Then it's kind of starting to pick up speed here now. And then by the end, it's just skyrocketing. Wah! So, again, if we could have infinite resolution, we will. And maybe someday we will. As, you know, computers are getting more memory and faster CPUs all the time. So we'll be able to keep pushing this boundary. It's just that, again, to get double the resolution, we need 8 times as much memory, 8 times as much power to push it all around. It's not double the memory, it's 8 times the memory. So it's kind of a wall that we're hitting. So in any case, so that's what voxels are. They are areas of space that store something. For our volume simulations, we're going to be storing whether the object exists there or not, how much of it exists there, let's say from a scale from 0 to 1, or even beyond. And then we're also going to store the direction the air is moving and how fast it's moving. So we're going to actually have 2 different volumes. One that stores the presence of the smoke, because this could be a smoke sim, and one that stores the speed and direction, which together is called the velocity. So that's voxels. So we know what voxels are more or less, and now I wanted to show you this is what they will look like in our viewport in a real sense. This is the fog like we were starting to make in our scene. Again, just follow along with me, or just watch. Don't actually follow along in your scene. So here is a fog pig. You can see we can kind of see through it. It's a fog. There's values being stored here. And what are those values? So I made a little sampler thing here. Density is what we refer to the value stored at any given voxel. Now remember, there are a lot of voxels here, and that's why it looks like that. If there were less voxels, you can kind of see the cubes a little easier. But as I increase this here in my arbitrary scene, this is just the timeline. Don't think that this is normally what this does. This is just what frame we're on. I've tied the amount of voxels to what frame we're on. In any case, so I made a little sampler thing here, and as I move it through space, it's saying how much density is where my sphere is. As I move it in, you can see along the border, there's not quite 1. And then once we're inside, the density is 1 at any given voxel that we're asking for. So it's 0 out here. It's 1 where there is a voxel that we can actually see. And then sometimes there'll be like a value in between that. So you can see right here on the edge, 0.24 apparently. There's kind of a transitional area where it's not quite 0. It's not quite fully opaque. It's not quite nothing. Again, density can be higher than 1, but for the sake of our purposes, 1 will be the opaque area here. So that is that. Now, that is storing, again, the presence of smoke, how much smoke is at a given voxel. Now, we can also store direction and speed. And those are called vectors. A vector is simply a direction, meaning point this far in the x direction, left to right, let's say, this far in the y direction, up to down, and z in the depth sense. So it's a little arrow, essentially. It's a little arrow that's points in a direction. And depending on how long the arrow is how fast it is. Now this is what velocity is in math in general. It's a direction and a speed. We often in common English think of velocity as just being the speed, but technically speaking it's also a direction. So you can see I can move it around, and so it's just an arrow. I just want to demonstrate that it's an arrow that can point in different directions, and that's pretty much it. It's x, y, and z value. Much like a point in space, like where the sample is at some location x, y, and z, a vector is also 3 values, except it's not denoting a point in space, it's denoting a direction in space. Now in this example, my arrow is only ever 1 unit long, meaning if you were to measure from the base to the tip, it would be 1 unit. So you can kind of see that here, where it's pointing straight up and down, y is pretty much 1, and x is pretty much 0, and z is 0. Now again, these arrows can be longer than that to incorporate a speed element. A arrow that is 3 times as tall denotes a air that is moving 3 times as fast as the one that is only 1 unit vector long. So let's combine these two concepts. Turn all that off. We have here, I'm going to move back into my 2D camera for this. Here is a, come on. Here's a grid of voxels. These squares, all these squares. And you can see we have vectors in each one. And obviously they're not the same from square to square. You can see that they are all similar to each other. So they kind of change direction over space. That is characteristic of the way air moves. Typically you don't have one cell, let's say it's one discrete area of air that is pointing the opposite direction as another one. That's called divergence, and that is something that we are trying to not have. When we're doing simulations, any kind of fluid simulation, that's what it is doing for us. The kind people who wrote the smoke sims, the main job they have is to prevent that from happening. We want these kind of smooth flows. So in any case, this is called a vector field, meaning it's not just one, it is many of them, and they take up space. Now we're looking at it as if it's a 2D slice right now, but it's, just imagine there's depth also. So what does this all mean? Why do I have all these little red dots? Well, the red dots will show you how they have a position and they're going to want to slide along the arrows and go the directions they're going. That's the point of advection. Advection is a term that simply means to move along a velocity field. So as I moved forward, you can see these points up here are kind of doing that kind of curve here. These points here are going to the left here, and so on. They are just kind of sliding along this velocity field. So I hope you are seeing how we're combining these concepts together now, where we have discrete cells of air, which are called voxels. The voxels are storing data, in this case, the direction the air is moving in, and that data is represented as vectors. So vectors in a vector field are moving these points around. Now, this is a smoke sim, and we've been talking endlessly about the density that is also stored. So for the last one, here it is again. Actually, I gotta keep that on. Here is density. Imagine this is the pig head, but these are just some spheres of fog. They move in the exact same way. A little slower though, apparently, but they move this whole same way. The particles are just to kind of give you an easier way to understand how specific positions are moved along a velocity field. The fog, the density values, are moved the exact same way. So that is how, if we can make some kind of velocity field through various means that we'll get into in a moment, we can then move our density, aka the fog, along there to create an interesting simulated effect. Now, technically speaking, let's get a little bit more into the weeds. The velocity field, as you can see, is not moving. It's just staying. In reality, in a simulation, not only does the density move along the velocity field itself is advected through the velocity field. So I didn't make a demonstration of that, but it's a little more advanced. The idea simply is this vector data moves too. Much again the same way, if you imagined you sneeze, first there's speed right outside of your mouth, then a moment later there's the wind further from your mouth is also moving, and so on. The speed itself moves through space. So, but again, I didn't make that here. But I think you get the idea. Very proud of these little demos, so I really hope you like them. It's the main reason why I wanted to re-record this lesson, because I thought these came out pretty good. Cool. So let's get back to the actual project. All right. So here we are again. Very cool. So that's what we were doing here. We were, with the VDB from polygons, we were creating the density volume, which we could kind of see here. Now, we can see it easier. Right now, there's not that many voxels, is what I should say. If you middle click and hold on this, you can see there's only 19 by 19 by 22 voxels with a pitiful 2,000 voxels, which is pretty much why it looks like a blob that we can barely see. Now we can create that, we can make that have more voxels by, for example, if I reduce this by half, there will be 8 times as many. Because again, there'll be twice as many on every axis. I could reduce it again. Now it's starting to fill it up more, and we can really start to see it. Now, thin areas like these ears are always going to be kind of translucent because, you know, we're looking through many cells of voxels going away from the camera, which builds up this opaque nature of it. But, you know, it's not looking too bad. In fact, it might be a little easier to see, though, if we make the background be black. So I'm going to press D in the viewport to bring up the display options. And if you click background, you can change color scheme to dark if you're not already doing that. So now we can kind of see it a little bit easier. I'm also going to turn off this ground grid here by clicking this. And finally, I'm going to turn off this template thing. I don't want to see that anymore. So you can see we do have that. If I middle click and hold, be very careful with this, middle click and hold, if I change these values a little bit, like I move it up, you can see I can change the values on the fly like that. If you make it too small again, you're going to run out of memory, so be careful, or at least your computer will freeze up for a little while it tries to calculate how many voxels it needs. But again, this is just to demonstrate that the smaller the voxel size, the more voxels there are. Because this fixed distance or area is being divided. If each voxel is smaller and smaller, there'll be more and more. And if there's more and more, we get it to be denser and denser, densely packed. So there you go. So now we have the pig head proper. You can actually get some lighting into it. If I come back out here to the main area, I can click skylight. Now there's it makes two nodes that I won't really get into too much. Basically it makes a sun here. It makes a skylight, which is this whole environmental thing here. I'm going to turn off enable light and viewport so that we can still see it look black. But now we actually have some shadows, which is nice. If I turned off the sunlight, you can see we lose the shadows, but now we have some shadows. It helps to see it a little bit better. Wonderful. So there you go. We got a nice pig head. One last thing we want to do before we actually move on to the simulation itself is let's go in here and drop down a null. A null literally does nothing, hence the name, but it's a nice little marker to point to. Our simulation is going to ask for a node to load into itself, and we don't want to like point to this, because if we pointed to this and then we decided to like actually we should move it later and like rotate it or something, you know, if the simulation is looking at this, it's not going to see anything that happens after that. So typically what we do is we make a null that says this is just some generic whatever, and anything that happens before it will be considered now. And we're not going to actually do that, but there you go. Something else I wanted to point out is the idea of takes. You can see we already have this take list tab here, but if you don't have that for some reason, you can always go to plus, new pane tab, type take list, and then there you go. Takes are collections of overrides. Right now, we have, you know, various nodes with various settings on them, but we can store a collection of overrides. So right now, let's consider when we're in the main take, which is the default take, that we're in, let's say, low quality mode. So I'm going to say this can be here, low quality. Boo, look how low quality that is. Gross. But then if we go into take list, I can say add take, double click on that, call it HQ. And in HQ mode, I can say, see now I can't change anything. But if I right click and hold here and say include in take, I could change this to something else. So now this node, or this parameter rather, is active, and you can see it here in the take list. HQ mode now consists of this specific parameter being set to this specific number. If I go back to main, you can see it went back to the original. 0.05. You can also do it up here. That's what this is. HQ, it goes into high quality mode. So now I can just work in low quality mode, which will be easier on my computer's memory and on the CPU. And then when I'm ready to do something crazy overnight, let's say, like I might run a simulation that takes 8 hours. All of that, it takes 8 hours because it needed a lot of memory and CPU stuff, and I don't want to deal with that while I'm working here. Not when I can just easily work on a low quality version and just switch it over to the high quality version when I don't need to use my computer. So I'm just going to say that. Go back to that for now. So that's another little convenient workflow tip for you there. And now with all that set up, we will get started with the simulation itself. So before we get into the simulation itself, one more thing to set up in the scene might be a ground plane. So come back out in here to the object area, tab, and make a grid here. A grid is really just a plane, a flat plane here on the ground. I'll call it ground to that effect. By default, it's centered at y is 0. There you go. But it's kind of, our pig head is kind of just sliced there. So what I'm going to say we do is let's raise up the pig head. So let's go in here into source. Let's make sure that we can see everything else here. And let's move this up. So I'm going to say middle click and drag it up. Right now, that's probably about right. I want it to be just, you know, hovering above the ground. My hope is that when we run the simulation, you know, it'll apply some turbulent velocity to move the smoke around, but maybe some of it will hit the ground and kind of like push against it or something. That might be nice. So now that we moved everything, we need to update our camera also. So go back into your camera, click on the lock, move it up to here or something like that. I don't know. It doesn't really matter. But just give us enough space that we will see it hit the ground maybe, and we can also see it go up. So again, we can always update that later again too. Let's also have the back, because we're going to render all this. We're going to render the ground plane. I want it to kind of curl up in the back. Let's rotate it a little bit, like so. Maybe move it over a little bit. And then I'm going to go into it by double clicking on it. I'm going to press S for selection mode, which is this arrow here. I'm going to press 2 for point mode, which you can do from here. You can see points is 2. And now that I'm selecting points, I can just click and drag over them. I'm going to press T to translate them up, like so. I'm going to come back into my camera here. This is the renderable area again, just this, not this grayed out stuff on the top and bottom. So once I get out here, I'm okay. So now I have like a nice little backdrop. And I'm going to change primitive type to NURBS. I'm not going to explain what NURBS are, except to say that they are, it's a curvy kind of surface that's defined by these points. Instead of the very literal points of a polygon, NURBS are like, well, you know, try to hit these points, but don't worry if you don't. So there you go. Kind of a curvy look to it. Great. Save that. And there we go. I'll just hide it for now, but we know that it's there. And there you go. So now we're all set up and ready for our simulation. All right. So to make our simulation, we need to press tab here and say DOP network. DOPs are dynamics operators. Everything up until now, inside here in the geometry land, when we're inside of these geometry nodes, they're called surface operators, also known as SOPs. Now, surface operator makes sense for this because this is literally a surface, a hard surface. Why are volumes called surface operators? Well, volumes can technically represent surfaces, even though this one doesn't really. It's a, you know, thick cloud, which doesn't really have a surface. But that's the way it is, so that's the way it is. So deal with it. Now, moving on, here we have dynamics operators, which are not building up any kind of geometry or volume, but they are instead running some kind of simulation. The simulators themselves are called solvers. And here we see all kinds of solvers. There's rigid body solvers, liquid solvers, smoke, blah, blah, blah. And we want the smoke one, which is actually, you will see a smoke solver. Don't use that. Use the pyro solver. Pyro solver basically includes the smoke solver, but adds a lot more functionality to it. And even though we're not going to do anything with fire, aka pyro, we might as well just get used to the fact that we're going to use the pyro solver in every, you know, ensuing lesson here. So there it is. So there's the pyro solver, which is literally the mechanism or the engine that moves the data around. Now the data itself is stored in a different node called a smoke object. You'd think it'd be called a pyro object, but it's not. So there it is. So this is a container that will store our various volumes. That's going to store our density volume, our velocity volume, and many other things besides that only the solver cares about that we don't really need to know. But this is storing the data. This is acting on the data and changing it. And then this output, much like that null from before, is kind of just a marker that says this is the end. It also you can cache files out with it, but we're not going to. So there you go. Now, first thing we need to do is change the shape of this. This is going to be the air, the container that stores where the simulation is. So we need to find some kind of bounding thing like this will accurately capture what we're trying to do. So make sure this is in show all objects, which apparently it is. Let's turn our pig head back on so we can see it. Now it's not in the simulation yet just because we can see it, but we do need to, you know, control the bounds of this so that we obviously have to at least capture it, but we also want to have more space around it besides so that it can move around from here. So it's not even capturing it there. So something like that, it's probably still too big. I'm going to say, first things first, however tall it is, let's make the center be right in the middle of that. So go to right-click and hold on this and go to copy parameter. These are called parameters. And go right down to this one here below it and say paste relative references. We now have a little expression, aka a bit of a script, that says, instead of typing a number in here literally, just look at the number from the other parameter. And I want to do that because I actually only want half of that. Half of that number will center this whole box right on the ground. So this is y equals 0 is going to be the bottom plane of this box. Because if this is 0 and the center is 1.25 and 2 times that is 2.5, which is the size, the whole thing is resting on the ground. You could also just type 1.25 there if you wanted. But this is convenient because now as I change this, you can see it stays resting on the ground no matter how high it gets. And I want that because I want a closed boundary. I want the negative y to be the only one that's checked on. That means that it will automatically collide with the ground. And again, we have a ground. When we render it, I want to see the smoke hit the ground and maybe roll off of it or something like that. This is a very cheap and easy kind of collision to do. It's fast for the solver and it will, make it look interesting anyway. So as far as the size goes, the bigger we make the domain, like I said earlier, the more voxels. The simulation also has voxels. It's not just our source. Our source populates voxels with starting values, which is, the density where the pig head is. But then they will move out into the simulation, which is also storing the current density and the current velocity. So the same thing applies to the simulation. The more resolution, the more voxels we have, the slower it's going to run, and the more memory it's going to take. So let's try, if I don't anticipate that it's going to fly all the way over to here, then there's really no reason for me to have it be this wide. So instead of 5 wide, let's make it 4 wide. And similarly from front to back, the same thing applies. So we can make that 4 also. And that's probably fine. So good. That's, I'll just zero these out too, for the sake of it, making it easier to follow along at home. It's there. Something like that. So save that. Now, again, this smoke still doesn't actually exist in the simulation yet. We've just used it as a reference to set up what we were doing. To actually source it in, go to the smoke object, initial data, seeds density SOT path. I'm gonna make this a little bigger for a moment. We can either look for it by clicking on this button and saying, well, here's the source, and there's that source null that we made. Or, well, the nice thing is, if I have that open over here, I can actually literally click and drag this to here. So now you can see in our simulation, there it is. Remember, when we clicked on this, we were still seeing this node. Now we click this, now we're back in the simulation again. We could, at this point, probably just permanently link this view to this. That way, if I click here by accident, I don't accidentally not look at the simulation. So there you go. So now we literally have it here. And if we press play, it will literally run. And we've now made your first simulation. I hope you enjoyed Apply Houdini Volumes 1. Make a pig head disappear, and that would be a terrible lesson. So let's keep going. One thing we want to do is we need to determine the resolution of the simulation. Right now, we have a division size of 0.2. Now over here, we had a division size of 0.05. So the incoming density is actually much higher resolution, because the voxels are smaller, than our simulation. You can see if I were to match that, like so, now we're actually seeing it better. Now if I were to overshoot this, like so, we're not going to see much improvement, because this is already, the incoming volume itself was this resolution. Because I have a high resolution in my simulation, that's fine. That will help maybe with the velocities as it moves around, but the pig head will be just as, let's say, coarse or chunky. So let's, at least for a second, go back to that. I also want to take a moment to multiply the incoming density by some number. Here I am multiplying it by 10. It's a lot easier to see now. Now it is actually changing the values. The density values are literally 10 times larger now. But because of that, they are more opaque. They're harder, because there's more density. Basically, it's like thicker smoke. It's harder to see through. And that is, I think, desirable in this case. So now let's make our simulation work a little bit more dynamically for us. Right now, we're doing everything in terms of the size of the voxels themselves. That can be a little unintuitive. What I often like to do is, instead of doing it by size, let's do the division by max axis. So that means let's denote how many voxels. For me, I'm usually comfortable running a sim, like developing a simulation on my computer when there are 300 voxels across the largest axis. And then when I want to do my high quality one later on, I'll do 600. So let's do that. Let's go into the high quality mode and include this and say when we're going to do our actual sim, let's do 600. And let's go back to the main here. Now, the simulation is 300 voxels wide. Now, I don't know how big is that? Like, how large are those individual voxels themselves? Well, the max axis, these are the axes here, X, Y, and Z. Apparently 4 is the maximum axis. Both the X and the Z are that number. So technically speaking, we could easily figure that out, where we can say 4 divided by 300 voxels, 0.01. So you can see again, the incoming size of the voxel is too big. In fact, it's much too big. Let's dynamically have this number reflect the optimal size. So let's do that calculation on the fly that we just did. So I'm going to copy parameter, which is the max axis, and I'm going to say paste absolute references. We did relative before. I'm going to say absolute now. There won't be any ... / stuff like this, which is like a Unix style thing that I won't get into. So now the voxel size is 4, which is huge. We don't want that. We wanted to say 4 divided by how many voxels there are. So copy this one too. Copy parameter, go over to here, go to the end of the line, say divided by, and now do paste absolute references. Now if I click on this, we should see that should evaluate to the number that we just saw. 0.01333 or whatever. If I middle click on that, we can see it's 150 voxels approximately on each axis. And this is 300 voxels. That's still correct, because remember, there are many more voxels besides that in the scene. It's not just the original source, it's also all this extra space. And if we change it to high quality, we can see, oh, actually we need to do, so that's important that we did that test. Right now, this is still overriding it. So while we now have this cool expression here, in HQ mode, let's get rid of that. To do that, we can right click and hold here and say exclude from take. Now it will go back to not being a, come on. I don't know why it's not doing it. Just go here instead and find it. VDB from polygon, just delete it there. That was weird. Oh well. Anyway, now it is even smaller. See that number in there? If I go to the main, you can see it's double it. So now on the fly, we get to do that. So that's pretty cool. We can switch back and forth between main and HQ. So there is our simulation. If I were to run it again, it's slower than it was before, but you know, it's not bad. It's still just disappearing though. So let's do something more interesting than that. Okay. So here we are again. As I was just playing, you know, it's going a little slowly. If you're a fortunate person and you have a really nice graphics card, we can speed this up considerably. If you go to the Pyro Solver and go to Advanced, turn on use OpenCL. OpenCL is a language that allows you to run these operations on the graphics card instead. And look how much faster it is now. Significantly faster. This is limited by the memory on your graphics card. So, you know, the 300 might work, but if I go to HQ, I might run out of memory or something. I'm not even sure. As you can see, it's up. See, look at that. This means basically that I ran out of memory. And I have an 11 gigabyte card as of the recording of this. So it's often not possible to take full advantage of that. So, you know, maybe by the time you're watching this, you'll have a crazy graphics card that I don't have. Or maybe you already do. Who knows? I'm going to turn this off. But that's what that's for. Watch out for that. In fact, I'll turn this on here. And then in the HQ mode, I will include this in the take and turn it off. How about that? See? Fancy. So now we can take advantage of it while we are in front of the computer. And although the results of the sim might be a little bit different because it will be running a different kind of instruction set, I mean, for our purposes, it's probably fine. It won't be that much different. Awesome. Save. So there we go. Now let's actually add velocity to it. Let's actually have it do something for once. So go to the Pyro Solver, go to Shape. In later lessons, we are actually not going to use these. These are built-in forces that are just kind of there for convenience. We can make much more complicated ones or at least access these in a way that we have more control. But again, for an introductory lesson, they're fine. We'll keep dissipation. Maybe we'll make it less. Dissipation is what's making it disappear. In fact, if I turned it off entirely, you'll see nothing really happens. Simulation is running, but there are no forces acting on it. Nothing is making it disappear, so nothing happens. So dissipation I've reduced to 0.05. Turbulence will actually finally add a velocity force to it that will move it around. Or does it? Because by default, we have... Where are you? It's trying to act on the temperature, which is yet another field. We talked about density. There's the vel, which is velocity. And you can see all these fields I should mention. If you middle click and hold on this, we can see we have a density field right now. Let's have the turbulence act on the density and not temperature. Temperature would be good if we were doing a, you know, fire explosion one, but we're not. So finally, we see spooky ghost. So that's something. And now you can see this blue bar here is how much cache we have in memory right now. So we can scrub it easily. It's not resimming it right now. But once it gets to the end of this bar, it has to simulate. That's pretty cool. It occurs to me that our scene is 240 frames long. I definitely don't want to run this for 240 frames. So click on this button all the way in the bottom left here. Let's change it to something much more reasonable, like 72. And well, if we ever want to, you can see how I'm reaching the end of my cache. So now all the earlier frames are being discarded. So if I try to go back to them, they don't exist. So that's no good. Let's use a flipbook to just take a snapshot of every frame that we can then look at. You can click and hold and go to flipbook with new settings. They're all probably, the defaults are probably all fine. I'm just going to say do it. So we'll get, as you can see here, if you're used to Maya, they would call this a play blast. But essentially this is just a image player that comes with Houdini that is storing a snapshot of each of these frames. So you can press play and have it do that over and over again while it actually loads it up. And that's something. This is convenient because I can walk away, come back, and see like, oh, is dissipation still too high? Is there going to be any smoke left by the end of the frame range? Maybe the turbulence is too high or something. I don't know. You know, right now it looks all grainy and weird, but that's just because it's in our viewport. It will actually render much nicer, which we'll do soon. But this is looking pretty cool. I'm not going to change it really from here. So I'm just going to close this and not wait for the rest of it. So come back to here. I want to demonstrate though, let's actually do a few frames again. If I middle click and hold on this now, you'll see there is a vel field, velocity. That's what we talked about earlier in the lesson. Those are the cells that store the vectors that determine the direction of the air. Pressure is that thing I also alluded to a little bit, where I talked about how the velocity field vectors should all kind of like blend into each other in terms of the direction they're going and shouldn't be like pointing away from each other. That again is called divergence, and this pressure field is something the solver figures out to ensure that the velocity flows nicely. That's based on something called Navier-Stokes equations, which you can look up if you want to have blood pour out of your eyes and ears. So we don't want to do that, but we do want to just at least see the velocity field. So click on the smoke object, go to guides. You can see by default the density guide is on. If it wasn't, we wouldn't see anything. It would still be happening. It'll still be, but we won't see anything. Let's go to velocity here and check out this. Or check this out, I should say. Whoa, crazy. These are velocities. These are velocities being charted over, I believe, 1 second. So if you started at the base of one of them and followed them, it shows where the smoke would move, starting at that voxel over a second. Now, if the velocity field didn't change otherwise. Now, it's kind of hard to see this. There's so many. There's one per voxel, and there's apparently 17 million of them. Now, it's only showing us one slice, as you can see. We can modify all kinds of behavior for this thing. So click on the vel, really it's supposed to say velocity, guide, and you can see we can change where the plane is by changing this slider. You can see how slow that is because it has to draw all those lines. Just keep it at the default of 0. One really nice thing you can do now is override divisions. We don't need one of these for every single voxel. So if we override it, now there's only 10 on each axis, which is probably not nearly enough. So I'm going to say like 50 maybe. Cool. And now it's much faster. So that's pretty cool. Let's see what that looks like. Let's do a play blast. I'm still calling it play blast. I've been using Houdini since Houdini 10, and I still call it play blast. All right, so there it is. We get these awesome velocity field things moving around like that. So this is because of the turbulence. The turbulence is adding all of this whirly, windy business, and those velocity fields, again, are moving the density along with it. And that's how we end up with this cool, crazy dance here. So I'm sure you're convinced. It seems to work. You can see how some of the smoke is hitting the ground. You can see right there it's pushing against it very slightly and subtly. Oh, maybe this plume will reach it. Looks like it's just about to disappear. No, it kind of hits it. Yeah, it definitely hits it. Cool. So we got our first collision too. So that's something. Save that. We're basically done with the simulation. Obviously, we'll talk in the next lesson about how to make a much more interesting simulation. But for now, I'm going to say make one more geometry node. Here we go. We'll just call it output. Turn these off. So output will get the data from the simulation. Right now it's just living inside of this simulation box. We need to retrieve it. So say dop import fields, point to that simulation, the .NET itself. The object is this one. If we middle click and hold again, it's called smoke object 1. The smoke object 1 is the container that contains these subdatas: pressure data, velocity data, density data. So this is the object, these are the subdatas. So with that in mind, the default object is that one, the smoke object 1. You can also just use wildcards. I can never remember what it's called, so I just do like smoke. Just give me anything that starts with smoke. Then here, we ask for this subdata that we want. So density. And there it is. That's the solved data. And now we have it. Same thing. We're not in the simulation right here, but because we're asking for data that doesn't exist yet, it's triggering the simulation in the background to run. Like so. Now, I'm going to drop down a node here called a file cache, which does kind of what you would expect. It's going to literally cache. It's going to save this data to our disk somewhere. So I'm just going to delete all of this and say $job is that project directory we set up all the way back in the beginning. I'm going to say /sim, which is just some arbitrary folder I just made up. And then we'll call it simulation dot version 0 in case we ever do another one, which we won't. $F is another variable, which simply means the current frame number. BGO is Houdini's native file format for storing data, geometry data, which could be, again, polygons or points or lines or volumes or whatever. And .sc is this fancier version of it, which I won't get into. So if I middle click on this, you'll see the current frame is here. See, it's version 0.1.bgo. Middle click here, v0 $F. $F evaluates the current frame. As I scroll through here, you'll see the number changes. In this way, we can simply save to disk, and it will do it. You can see it skipped all the way to frame 20 because it already had the first 20 in memory. So it was easy enough to just pull it from memory and write it straight to disk. For the rest of these, you can see it's running the simulation itself. I'm going to interrupt it. I don't want to wait. If I click load from disk now, and you don't have to turn that off to run the cache. You can always have that on. I don't know why it's not on by default. You can see those are all the cache files that we got to until we ran out, and it can't find any. But there you go. Cool. So there's our cache. We'll always have it. You can see we lost the blue line, but it doesn't matter because now we're just reading these files from the disk. And I'll say out. It's just good practice to have a null for all of these things. Save that. Like so. So what will be nice to do now is go into HQ mode and then now walk away from our computer and have it do it. Because this is going to take longer. It's going to take 8 times longer than it was just taking because it's 8 times as many voxels, you know, more or less. So what you can do is you can either say save to disk and just have it do what we just saw where it comes up with a little dialog box that shows you it. Or what can be nice is you can go to save to disk in background. It wants me to save the file first. Save disk in background is convenient if you want to keep working. What it will do is it's going to launch a little scheduler thing here. And you'll see it. And this is a little job. It's like having a little render farm on your computer. It's running Houdini again as another process on your computer. And it will allow us to continue working here. So now I can still just keep going and doing whatever else. Now my computer is slower now because it's still literally doing this in the background. But I can keep working at least. If I need to do something that, let's say, I'm not running my simulation here as well while it's running in the background, I could continue setting things up, and I will. So save it, and let's set up the last bit. Okay, so although I did say save the disk in background, I realized that I'm actually going to need the cache to review and render and everything anyway, so I just let it finish. Could have just done it in the foreground, I guess. Anyway, here it is. Here's our cache. Looks pretty cool. Again, obviously it'll look way better when we're rendering it, especially considering that this is the HQ cache that we did too. So this will look really nice. Now, one thing I'm realizing though is that it's kind of off center. If I go to 40 here, I'm going to say, let's go into our camera. Let's move our camera. I don't know how this happened, but this will be better. So maybe your camera was already good, but mine wasn't, but now it is. Maybe. So cool. Now, one thing we also want to make sure is you can see that it's getting chopped off here on the top. Let's hide that. It's chopped off because that was the top of our simulation, apparently. I guess that made sense when in my old camera position, but now that I moved it, I need to ensure that I'm not getting any chopped off values there. That would look stupid. Wonderful. Okay, so I think this will be good. Although it looks like it's getting chopped off on the right here too. It's possible that it's so thin we won't even see it. Let's just cut to it now. Let us render this. So in order to render, we need to have things to render. And what I like to do here, as good practice, is let's not rely on these nodes, which have the things that we want to render, but what will be rendered is whatever the render flag is set to. So if I had changed it to something else, like if I put it here by accident, you know, it's trying to resim right now, and I don't want that. I want it to always render this node. So again, just kind of as a good practice, let's make dedicated nodes for this purpose. So we'll call this render smoke. And I like to make all of my non-renderable nodes here. Click on the color thing, make them green, and the renderable ones and make them red. It's just a thing that I like to do. And so what we end up doing here is just import the exact node that we want to here. So in our case, we can say the output, the null here, import that into here. And that's it. So now this node, when we render this, we'll always be rendering that, the one that we wanted. Similarly, for the sake of completeness, although we probably don't need to go this far, I'm going to just do one for the ground as well. So same thing, come in here. Object merge is the node I'm using here, which basically says go get something from somewhere else and put it here. So here's an out node on our ground plane. Put it here, and now we have it. We need to transform into this object, or else we won't get the transform values from here. As you saw, it didn't work. And looks like it's a little bit off screen here. Let's move that up, not like that. Let's move it over a little bit. I didn't want that little gap that we saw there. Okay. So there it is. So we have our two render nodes. Although let's make it red. Really should just have this be wider here, so I have to keep resizing these. We got those. We got lights. We've got camera. We literally have action. And what we don't have now is a render. We don't have a render node mantra, like so. And what we want this to do is say render the frame range out, 1s and 72. Go to objects to tell it what to render. Right now it's going to try to render anything that's turned on. We don't want to do that. We want it to only render under force objects any object that starts with RNDR, which again are these two. So RNDR underscore asterisk will find these nodes. And if you're not sure, you can click this and you'll see that they're highlighted. So that's kind of cool. So it's going to render those. It's going to use any light that it can find, which is fine. We're never going to have lights that we don't need, at least not in this lesson. The camera is the one that it finds here, cam1. So that's set to. And we could go to render view right now and click render. And this will give us a kind of quick, lower quality approximation of what we're going to see in the final render. I'm going to zoom out here a little bit. So we're getting somewhere. We have a thing. We have the pig head here in all of its density glory. We could click to any other frame like this and it will automatically re-render. So it's going to load that cache. You can see it's dissipated pretty well by now. Maybe we'll go back a little bit. One thing I think we can do to help this is let's go to the material palette here, which again, if you don't have it, click the plus and then go find it, like so. We want a material for our smoke. Also click pause on here so this doesn't keep happening. Let's go get a basic smoke because that's what we're doing here. And let's also make a principled shader so that we can add color to the ground. So to apply those materials, render smoke, you can see under the render tab, there's a material. So simply put under the matte area, matte for materials, put the smoke there. And for the ground, same thing, put the principled shader here. You can go to here and click on these, although I find, as it is doing now, there's something buggy about this, where it says 2 nodes selected. I don't know why it does that. If you come here and go to the matte area instead, we can click on them specifically. So let us render, let's have it start over again, and let's see what we have now with our 2 new materials. One thing I know is going to happen is that the principled shader by default has reflectivity turned on, which is not really what we want. So you can see it's super shiny. We're getting this crazy blowout light here. Let's go to the principled shader surface area, turn the reflectivity down to 0. We don't need that. The basic smoke looks a little bit better now. This is using the actual, I mentioned Pyro Solver before. This is the Pyro shader. This is literally made for, rendering smoke. So it looks kind of nice by default. Let's take the principled shader here for the ground. It kind of blends in with the smoke too much right now. So let's find a color. I'm going to click this orange thing here. That's too crazy. Let's make it. This is kind of like a mustardy sandstone look maybe to it. I just want it to have some nice color to make it, and then have it not be so gray. I want the smoke to pop off of that. Cool. So that is looking good. Again, we can click onto any other frame if we want to see what it looks like on those frames. We can also mess with the smoke itself. Like, let's say if you thought that it was too dense, we multiplied the incoming density into the simulation before by 10, but you can also just do it here after the fact. I can multiply it by another 10, and you'll see it's going to get way more dense now, which, I don't know, it's interesting. I don't know that it's the look that we want necessarily, but it's like lint now almost. I'm probably just going to leave it how it was. So I'm going to go back to revert to defaults, back down to 1. So that's cool. We could even change the color of smoke if we wanted to. You could change it to blue. That might be weird. I tend to find that the colorized smoke doesn't really look very good. Nothing wrong with Houdini or Mantra. I just think that it looks bizarre. I don't know, this kind of looks okay. Maybe I'll keep it like that. And after all that. That looks weird to me. It looks better when it dissipates. I don't know. I'm going to leave it the way it was. So once again, I'm just going to right click here and go to revert to defaults. Something like that. Just keep it looking like smoke. Was that even the default color? I don't think it was. I'm going to Control Z it back to where it was. Oh, it was white. Okay, so there you go. It's done. That's it. And all we need to do is actually render this out. So I'm going to stop it here. This is, again, that's just the preview mode. Save this again. We can render it here, going to render to disk. It will save it to whatever you have specified here. The default is probably fine. It's going to save it as an EXR file, which is good. That's the kind of the industry standard file format. The $F4 means it will use the current frame number, but will padded to 4 digits. So you see we have 2 zeros in front. That can be helpful for some compositing programs to read it into. HIP name is, of course, the name of the HIP file, which is this. So as you save new versions, it will change here too. OS means object string. That refers to the name of this node itself, which is Mantra 1. So you can see all of that when I middle click on it here is there. The name of the file, the name of this node, the current frame number, and the industry standard EXR. Let me think. Am I missing anything? That's probably enough. I mean, obviously, we'll talk more about all kinds of render settings and simulation stuff in later lessons, but I think this is probably good. So without further ado, let's run this. I guess I might as well mention the resolution is actually here on the camera, 1280 by 720. If you wanted something higher, you could go like HD TV 1080. That would make a much larger picture. I think this is fine though for our purposes. It will be a slow render. The render itself is slower if the volume is dense. Like we're doing the very high density one, so it's gonna take longer to do, but it'll be worth it. So anyway, enough talking. Render disk. And here's our final result. We have a pig disappearing into thin air. And that's it. As promised, a bit of smoke in the shape of a pig moving around in a smoke simulation in Houdini. To load this up, for the record, you know, we just run mplay, which is a separate program that comes with Houdini. That's just simply the media player. And then file open the EXRs wherever you save them on the disk, and then there you go. It'll just load them all up at once. And yeah, so we did it. We learned about voxels, vectors, smoke density, volumes in general, simulation setups, cameras, lights, materials, all in one easy lesson. In the upcoming Apply Houdini Volume series, we'll also learn about all the complexity of actually sourcing smoke dynamically and all the cool forces and micro solvers they're called to move things around in a more interesting way. All the details of rendering in terms of optimization and just getting to look good, shading explosions, all that good stuff. So check that out. I hope you enjoyed this lesson, and let's just bask in this cool effect a few more times. And that's probably enough. All right, until next time. Bye.